Okay, this video is for 8.6a, graphing cubic functions. So last week we talked about graphing square root and cube root functions, and now we're going to do the opposite of the cube root functions, which is graphing cubic functions. First thing we want to do, and to remind ourselves some of the stuff we talked about today in class, is to be able to identify what type of graph we have based on the equation they give us. So let's start with problem maybe 1a and 1c. So problem A is a square root function. You can see the radical, and since there's not a 3 on the radical, it's a square root function. That's problem A. And the graph that matches up with our square root function is this one right here. It starts at 2, 0, and it arcs upward from there. Next, let's look at C. This one's not square root, there is no radical, so we know it's also not cube root. And because we can see that that quantity is squared, that is a quadratic function. So the quadratic function is C, and we know that quadratic functions make parabolas similar to this graph right here. And so this is our quadratic graph. Now, let's move on and actually graph a cube root function. One thing to remember about cube root functions, and it's similar to what we talked about last week, is cube root functions have a general form. And that general form is going to be something like this. Or cubic functions have a general form, and it's similar to what cube root functions have. And that general form is this. Y equals a times x minus h cubed plus k, where h comma k is the point of inflection, and h describes the shift left and right, k describes the shift up and down, and a describes whether or not there's a reflection over the x-axis. So if we take a look at this equation here, y equals x plus 4 cubed plus 6. Since it's plus 4, the point of inflection, or the shift left and right, is opposite of that. So our point of inflection begins at negative 4. And then for k, that stays the same. It's not opposite. So negative 4, 6. That is our point of inflection. And then that is the point we're going to want at the center of our table. And from there we can build other values off of that. So we'll go a little bit above it, a little bit more negative, and we'll go a little bit less negative. Now if we plug these remaining values into that function, if we plug negative 3 in, we get negative 3 plus 4, which is positive 1. Positive 1 cubed is positive 1, and 1 plus 6 is 7. If we plug in negative 2, negative 2 plus 4 is positive 2. Positive 2 cubed is 8, and 8 plus 6 is 14. Same thing going the other way. Negative 5 plus 4 is negative 1. Negative 1 cubed is also negative 1. Negative 1 plus 6 is 5. And then negative 6 plus 4 is negative 2. Negative 2 cubed is negative 8. And negative 8 plus 6 is negative 2. Now that we have these 5 points, let's graph them. Negative 4, 6 is at this point right here. Negative 5, 5 is right here. Negative 6, negative 2 is right here. Negative 3, 7 is right here. and negative 2, 14 is somewhere off this grid, somewhere very high up there. Once we've drawn that, we can connect the dots, and we know that we have a graph that looks somewhere like that, where negative 4, positive 6 is our point of inflection. Just a reminder, the point of inflection is the point where the cubic graph will bend. And now if you take a look at the domain and range piece, every single number can be plugged in for x. There's no limit on that. And if you look at the graph, you can see that x can decrease forever and increase forever. So our domain is going to be all reals. It's a little more obvious with the y. You can see that this graph is growing very high and very low depending on which side of it you're at. So there is no limit for the y values either. So our domain is also all reals. For the remainder of this worksheet, apply sort of what we talked about in this problem to try to understand some of the other cube functions.